All right, here we go. Let's try this thing again. Anyway, what you see on the screen is the objective was to dramatically increase network stumbling coverage by providing line of sight as large as possible to all the targets in the area. The concept, use a high-powered rocket as a boost platform for either an access point or small computer. At the peak altitude, what happens is the parachute deploys, comes out where there's a seam in the rocket. You can see it about 3/4 of the way up to the top. And the next part of the plan was to establish a wireless distribution system linked from the rocket access point to a launch site access point. WDS stands for Wireless Distribution System. It's used by a lot of WISP operators, and it's simply a means to establish a dedicated AP to AP bridge connection. Once communication with the ground is established, we begin our net stumbling, transmit results to the ground computer. Pretty much everything you'd get on regular net stumbler, this in this case is coming from site survey information on the access point. Other tests for redundancy, we decided not to put 2 access points in the rocket. We used actually a little iPac computer with mini stumbler loaded on to capture data independently. The advantage, of course, is that if you shoot the rocket and you lose it, well, your transmittal data was good. If you shoot the rocket and you get it back, well, you got extra data, you know. So either can happen. I've seen both happen. Now I'd like to go through what I was thinking about as far as the design considerations when I envisioned this rocket back in February. Component section is critical here because everything from the AP to the parachute has to withstand high G forces. It also has to fit in the body of the rocket. Very important. It's a 5.5-inch diameter rocket. It was pretty hard to find components. I mean, obviously a laptop won't cut it. I attempted, yeah, exactly. Additional redundancy was built in everything on this thing because if it can fail, it will on a rocket. The launch vehicle, initial design consideration was it had to be capable of boosting a 3-pound payload to an altitude of greater than or equal to 1 mile. Large enough to visually track and recover. I think you can see it. Engine thrust to weight ratio, minimum 5:1. That means it can get off the launch pad. If you put a weenie engine in your big rocket, you can just watch it sort of go up and do like this. And finally, as I'm a member of EEE, we're very safety conscious. We've kept rocketry legal in the U.S. It's still legal in the U.S., and we want to keep it that way. So we did this under all the government safety codes. And yeah. Here it is, and yes, America, size does matter. A little bit about the Nike smoke. You may have seen the smoke at some of the military installations around the country. It was used for atmospheric research in the 1950s. Its prominent feature, the Nike smoke, was named that because it had smoke generators and had a real dense smoke trail. The other characteristic of it, which is notable, is it has extremely large nose, sort of a swollen nose cone. So, good for electronics. One of you guys asked about the rocket specs a little earlier. This rocket was designed using a simulator called RockSim. With the weight and stuff on board, the design altitude was 7,800 feet. Liftoff weight 18 pounds. The motor, an Ellis Mountain L330 maximum thrust engine. That's 95 pounds and an 8.9 second burn time, which is pretty much incredible for a high power rocket. I mean, that baby just keeps burning and burning and burning. Finally, the electronics had to fit in that 12 by 5.5 inch payload section, which happens to be the little short section under the nose cone right there. Electronics considered, high power AP or computer plus a card had to be, whoa, I'm glad we still have power. Okay. Electronics also has to fit in the payload section, small enough to fit there in less than 3 pounds. Power was a big consideration. Batteries are very heavy devices. If you put something up in space or wherever, then you can't have very big batteries on it because that adds every ounce to the takeoff weight. So we went with devices that work from 12 to 18 volts DC, pulling no more than 100 milliamps. Pulls a lot of amperage, then your batteries are pretty much shot in 5-10 minutes or less. Other thing that the electronics had to handle was capable of at least 10 Gs. Here's what we considered as far as putting in the nose of the rocket, an IPAC handheld. I initially rejected this one, but later bought into it because I found one on eBay. But these are expensive, and basically what I did is use an old style IPAC, plugged the MCIA card into it, and it did have an external antenna jack then, so I could hook it to the high gain antennas. The other consideration was I think Dell sells some computing tablets that were suitable. However, $2,000, probably not a good idea to put on top of your rocket. You could see it vaporize in just a second or two. Laptops, as my friend Nick Hopler says, forget about it. It ain't going to happen. And then various access points. This is the winning access point. It happens to be a deliberate access point. Deliberate makes high power APs. Coincidentally, they're one of the biggest suppliers in the U.S. for the WISP business. The specs for the access point supports 802.11b and G. Output power, 250 milliwatts on B, 100 milliwatts on G. Size and weight, 5 by 7 inches, fits perfectly in a 5.5 inch rocket. 12 ounces, it's a Zenwell radio, and there's the chipset. Has a bunch of advanced features on it, web managed, primarily of which we use the web managed user interface and site survey. Also has supports encryption, WPA, TKIP, WPA2. The onboard computer. I wanted not just an air-to-ground signal transmittal when I first designed this thing, but I also felt like I needed some redundancy to collect onboard data. In other words, what if this thing went off and we didn't get any signal from it? That's a distinct possibility with something traveling like 300 to 500 miles an hour. So I found an old iPad on eBay and purchased it. Got my idea from a hacker whose name was Blackwave. He was very popular. He was at Defcon back 2001, 2003 time frame. Many of you may recognize him for his purple hair, and I believe he was part of the Irvine Underground. He has vanished since 2003, so Blackwave, thank you for your stumbling rig and the specifications. We don't know where you are, but we really appreciate it for the rocket. Another piece of electronics on board the rocket near the top is called an Altec accelerometer and altimeter. Basically, the accelerometer calculates altitude just based on inertia. The altimeter uses a barometric pressure sensor to calculate the altitude. Nothing to do with wireless, however, very critical as it's the instrument that happens to blow the chute out at the peak altitude. Next, we'll move on to the design of the antenna system. This is a big deal because I don't think a lot of people think about radio propagation in theory when they think of 802.11b wireless. You put it in a room, yeah, you got your access point, yeah, it works. But actually, antenna design is in 3D is quite a challenging engineering process. The other thing was getting an antenna small enough and having a radiation pattern would fit inside the rocket. What we're looking for is to maximize the land coverage, minimize the sky coverage, there are no APs up there, and get as many dBm out of this antenna as possible. We used an antenna that was called a circular polarized antenna, and the reason we did this was that they're used for satellite systems, and circularly polarized antennas are very immune to Doppler effects and fading for moving objects. This is what it looks like. If you want to know the difference, it's pretty simple. Vertically polarized is what you have on most of your access points at the house. It's just, hey, I'm vertical here, look at me, and all the people you're talking to generally have the same antenna, which is I got this little antenna sticking up at the back of my computer. A lot of WISP operators in heavy trees using something called horizontal polarization. In this case, it goes on the horizontal beam. Reason for this, if you got heavy tree cover, you can easily shoot underneath the trees or underneath the canopy and get a lot better transmission distance as a WISP operator. Finally, of course, you have the circular polarized. There are two types of circularly polarized antennas, right hand and left hand. That's a right hand spiral, which is what we use. You have to have a pair of these in order to make them work right. Theoretically, the way these things work is that the incidence angle, pretty much you can have any incidence angle of signal, and the signal will not fade on when it hits that spiral on a circularly polarized antenna. This antenna is located right at the separation point of the rocket, that little seam you see near the top. You may recognize this as it's just a plain conference room antenna actually. It's to put up in a big room like this right in the middle of the ceiling. The patterns you see are what microwave engineers and amateurs use to determine where is this thing going to transmit. Horizontal, of course, is like this, so it's going to cover the room. In this case, it's going to cover the floor above and the floor below, because you can see it's got a couple null nodes to the top there, and it's got actually the right and left is up and down with respect to the room. See if I've got a pointer here I can show you. Well, anyway, the up and down are the right and left hand lobes there. And this particular antenna was hooked up to the iPad computer in the rocket. For the access point, which was a lot higher powered, I decided to go with an 8 dB antenna. Again, it was circularly polarized. Reason for this was I wanted a big cone under the rocket with as high gain and as much signal as I could get. Because what happens on this in wireless distribution mode, Dave on his computer on the ground was talking to the rocket, and then it was doing site survey going out in a cone-shaped area underneath. So that's what you're looking at here. It actually forms a cone underneath. Approximately 140 degrees, 70 degrees on each side, coming down from the rocket. Antenna coverage, as you see, 140 degree cone underneath the nose cone pointing straight down. And we're doing a few calculations here as far as the how far out it could go in the ground pattern. The math, basic trig here, you're looking at 53.6 square miles. That's assuming an altitude of 7,800 feet. Next slide. Okay. Thanks. All right. So anyway, this is just the numbers filled in. Basically, you got an 8-mile diameter circle here, which if you do the math, calculates to about 50 square miles. It's about all I could get with 8 dB. I'd like to do more, but we need bigger rockets for that. So anyway, that's what we ended up with. A pretty good swath of ground. The next design consideration is the link budget. And link budgets, you put in how much antenna loss you got, you put in the transmitter power, you put in the receiver sensitivity, plug all these things into these fancy equations, and it tells you, hey, number one, will your link work or not? You're actually going to see these access points. I mean, anybody can stand up with an antenna or put an antenna anywhere. It doesn't mean it's going to go 1,000 miles, okay? I think you guys know this intuitively. This is just a formal way to calculate that, and it's used for, link budget's used for microwaves, fiber optics, just about everything by engineers. So I calculated the reliability, the potential reliability for 2 links, one from the ground to the rocket, and the other going out from the rocket to all the target access points. Got tired of plugging in equations on my calculator, so I found a cool site on the internet that would do this for me. It's called swisswireless.org if any of you are interested in or setting up your own WISP business or whatever. Right here, hang on, let me blow this up. I can't see it on my slide. But the numbers here, basically for the transmitter, consider that as an access point target on the ground. The transmit output power would then be 50 milliwatts. Cable loss is actually calculated. I just plugged the number for the same cable loss I had on the rocket, which I figured you either got a antenna, you probably got an antenna directly connected to your access point anyway, and average 3 dB gain. Pretty much anybody that's got one at home, you've got that much at least. The reception numbers, that's the 8 dB circular antenna on board the rocket, the cable loss on board the rocket, and the receiver sensitivity. That's pretty good. deliberate, how sensitive it is, how much of a signal it can pick up. That's equivalent to an Orinoco card if you have one of those. Next is the Rocket AP to Wi-Fi targets. All the same calculations here, with the exception that we assume 3 dB on both receiver and sender transmitters. That one went to the backup IPAC unit. As you can see here, for the 50-mile circle, it says on the bottom, link will be near theoretical limit. Link performance will be bad. Well, we didn't really care about performance. We just cared about stumbling and seeing the AP. So big deal. Software I used. The web browser comes with, the deliberate access point comes with a built-in web browser, which was cool because all we needed was Explorer, and we could contact the rocket, do anything we wanted to on the deliberate software. We use HyperSnap 6 as screen scrapes. Basically, we're catching the signal from the rocket and just doing screen scrapes on it. NetStumbler 4.0 on the ground, Mini Stumbler on board the IPAC on the rocket. Access point setup. Here you see that we set delivering up for both B and G bands and set it up as a wireless distribution system. That simply means that it's got a 50-50 operating ratio. It operates 50% of the time as just a dedicated bridge link to the rocket. It operates 50% of the time scanning the targets on the ground. Another setup screen here. This just shows the power settings. We cranked this thing up to maximum power before we launched it. Screenshot. This is actually near my house. This is not from on board the rocket, but a screenshot of the actual site survey function that we'll be using during the flight. This will set to auto update. It's got an auto refresh screen, so about every 10 seconds we get a fresh update from the launch vehicle. Stumbling plan at max altitude. The parachute deploys. Antennas are now in the proper position. In other words, this thing comes apart. Antennas pointing down. It's all hanging from the parachute. That gives us about, with the size parachute I used, 6.5 minutes of stumbling time. And the reason I put in here that the number of targets decrease with decreasing altitude, it's really true, because think about it. If you got a cone right here and the top of the cone's the rocket, well, as you come down, your cone's getting it's getting smaller and smaller and smaller as the rocket descends. A few pictures of the construction. When I was putting this thing together back in February, I documented it. What you see on the bottom half there is the access point hooked to a board. Behind there is the actual altimeter, and the space that the IPAC, actually over top of it, and from your view, is the space that the IPAC computer fit in. And that's just an Ethernet cable hanging out of the payload bay there. This is the engine that went in the rocket. Unfortunately, I couldn't ship it today. The fire marshal wouldn't agree, and the airlines weren't real hip on it either. So it is a hoss of an engine. This is bigger than most of the kid rockets that I shot. It's you can see the ruler there. It's about 3 feet long, and the thing's about 2 inches in diameter. That's a honking lot of ammonium perchlorate, which we Rocketeers affectionately known as AP. The other thing about the rocket construction, and the reason I picked the Nike Smoke, is the nose cone functions as an antenna radome. For you guys that don't know what a radome is, it means that it's transparent to radio waves at a given frequency. You've probably seen these at some of the government ground stations and stuff. They're known as golf balls, the big enclosures. Well, those are made like that for a reason. They protect the antennas from the wind and stuff, and the signal gets through. This is just a picture of that. If you look about between, actually on the horizontal axis at 2.4 gigahertz, this particular nose cone is made out of Teflon fiberglass, which is, as you can see, lost transparent. And that's what it looks like, what you see up here on the front of the stage. After I found my IPAC on eBay, I decided that since I only had one big honking engine for the large Wi-Fi rocket, that I'd really like to shoot this at some other locations. So I just happened to have an older rocket that I built back about 2000, And I said, this will be good because I can get some smaller engines and we can do some shooting in some more places and get some more data. So we added what's called a PML Patriot missile. It's capable of boosting the IPAC to 2,000 feet, can be launched in much smaller fields legally and in more densely populated areas because you can shoot it, you know, for instance, in a city kind of park and not get in trouble with the law. This enabled 3 launch sites that we did for this project. One was the big one was in Culpeper, Virginia. The next one was in Centerville, Maryland, and the third was about 2 miles north of the UVA campus in Charlottesville, Virginia. And that's just the other 2 launch sites that I just mentioned. There's what the Patriot looks like. It's a lot smaller than this, but did a good job. Now I'm going to turn this over. One more thing. When we shot this thing up in Culpeper back on July 24th, you actually have to get FAA approval for anything over 2,000 feet. So we had to call in and clear the airspace over Culpeper before we set this puppy off. And my Triple E friends, it pays to have friends in high places because my Triple E friends all helped me out with this. Now, with that, I'd like to introduce my friend, Mad Hatter here. His name's Dave, and he also works as a security engineer for Tenacity Solutions. He was instrumental in helping me get this project off the ground. He's worked with the start and been at every launch, and basically he's in charge of all the ground electronics. And so with that, Dave's going to show you a video. The first part of the video you'll see is going to be the little rocket we shot for fun, and the next will be the big one, followed by sort of a slow motion slideshow that I think you guys will find pretty interesting. Take it away, Dave.
T-minus 5, 4, 3, 2, 1.
Okay, go, Mike.
Ready?
Go.
All right. T-minus 5, 4, 3, 2, 1. Come on. Come on.
I just lost it. Where is it?
No, it's in these low-lying clouds again. It's going to be dropping down here shortly.
Let me run up here on this hill.
I'll run.
Just walk. At least you know where it's at.
There it is. There it is. Right there.
And the kids saw it.
We're going out to go look for it here.
There it is. All right, just right there.
It'll stay out of the clouds now, Mike.
This was a big honk and zoom lens. It's actually out a couple miles.
Don't run through the corn.
Right here, Rick. Where I'm at. That's the spot in the valley. Come on up here real quick.
Oh, he's going to be in great shape. Along that road, where we were before.
Yeah, they want to try to not run through the clouds. Yeah. Just on the other side.
And we had to walk about a mile to go find it, searching through the farms that surrounded the launch site.
That was a heck of a point.
We found it in somebody's front yard, about 200 yards from the front of their front door. So the family dog was extremely excited. It's kind of what tipped us off to the location of the landing site. Was the dog was going a little loopy.
He drool on those cones?
Probably he licked the mud off there.
That's cool. We clean that for you. Hey, well, next time he takes the motor out.
That's a nice. That was enjoyable. We go there back to what?
All right, here we go. All right, so what you're looking at here are the results of the rocket chute. Well, hang on. Hang on, go back. All right, what you're looking at here are the results of the rocket chute. The rocket went to 6,800 feet. This data is from the onboard accelerometer and altimeter. That's that big red curve you see there. You see deployed detected, which is where the parachute came out. The blue is it achieved 367 miles per hour going up. The other piece of information we got from the altimeter, it hit about 6 Gs on takeoff. So that's the actual flight data. And here are the stumbling results for Culpeper. The default is the only access point that we picked up off the deliberate access point. However, I do want to point out this was picked up at an altitude of over 6,000 feet. We know that because we were taking snapshots as the rocket went vertically. It took off at exactly 10:32 a.m. and that file, which is snap 01257, happens to be about 26 seconds into flight. So that's how we figured out the altitude that came up. We did pick up another access point, which is from the IPAC. Tell you what, just get into the backup slides. All right. Here's the net stumbler from the same Culpeper chute. We picked up a Linksys at 2,000 feet. The other shots we did, this is the Maryland sod farm launch, and here are the APs we picked up there. Keep in mind that this is from rural America, okay? Most of these access points that we're seeing are on big farms, and they're way out where there is no DSL, there is no cable system, there's nothing out there. These are access points that were, none of which were visible from the ground before we shot the rocket. The final launch here was at Culpeper. I'm sorry, Charlottesville. We picked up a lot more, I'm going to show you a Google Earth of these in just a second. We picked up a lot more access points in Charlottesville. This was a much smaller city park. It's about 2 miles north of the UVA campus. Unfortunately, the last rocket chute, which was on the smaller Patriot rocket went up about 200 feet in the air, flipped over. It was a little too side heavy and also a wind that day. It cocked into the wind and went sideways for about half a mile and ended up in the woods. So that was quite a trek for me to get. Unfortunately, antenna pointing down in the ground as the rocket flies horizontally is probably not the best configuration to have. So now back to the, let me show you the Google Earth stuff. This is the Culpeper launch site, and what I want to, let me get my pointer out here. What I'd like to show you is where we took off from and where we ended up. The Culpeper site, the launch field is right there. That's where we launched from. And where we ended up was way over here near a house, about 2 miles away. That's a big trek you saw us doing through the cornfields and stuff. I mean, this thing was way out there. In fact, this field is huge. I think it's at least a 1,000-acre farm, and we ended up in this lady's backyard, which, the dog wasn't at all happy. The next launch site we did was on the Maryland sod farm. Some of you rocketry guys may know this as MD at Maryland Delaware Association of Rocketry launch site. The actual sod farm is right through here. That's where we took off from, and we ended up, it's a very small rocket, ended downwind in that field right there. So again, what I like to point out here is that you got a very few houses. If you look closely down through this region, there are a couple houses, and up through here. This area here is not actually housing. That's like different crops and stuff. And I do know for a fact that there are no DSL or any kind of cable or anything in this area. So that's your 50 square mile circle, which we picked up. Charlottesville, Virginia launch site. It happens to be a city park. Hard for me to see right here, but it happens to be a city park. About right through this region here. There's a big clear field, actually right here. The rocket took off there, ended up 200 feet on its side and ended up in these woods right here. As you can see, UVA campus is down through here. That was a target-rich environment. Unfortunately, wind didn't cooperate that day, and I didn't get much data. I got 7, 2 on the ground, 7 in the air. You know, we had to call it a day, unfortunately. But I was hoping for a slew of access points there. Here's the overall results. Culpeper, we found 2 APs. 1 detected at 2,000 feet by the IPAC unit. 0 visible at ground level. Maryland launch site. Of course, all we had was the IPAC on board there. That was 3 APs. Again, none visible on the ground. And in Charlottesville, Virginia, we had 7 access points and then only an altitude of 200 feet, if that, sideways. People are much more security conscious in Charlottesville, just about everybody. I had a stay-out access point. I have all kinds of weapon encryption going there. So, obviously, rural America's prime target if you can find them. But you wouldn't find these by war driving. We got 5 minutes. Okay, so the conclusion is wireless access points are scarce in rural America. Most are fed by VSATs, which are same thing as direct wave, small satellite dishes. WarRockets picked up target APs in both the remote Maryland and Virginia sites, the rural sites. None were visible on the ground. Go ahead. Pros of WarRocketing: advantage, locating hard to find satellite-based APs, possible military uses. I know for a fact that the government does this with much bigger and better stuff, you know, $1 million plus. We did it for $1,000 basically, including all the electronics. Potential applications: targeting Bin Laden, Mel Gibson, whoever he hates AP. You fill in the blank. Number 2, you live in Wyoming and always suspected there was that Starbucks cafe just over the next ridge. And number 3, why drive when you can fly? WarRocketing cons: it's expensive. Propellant costs $35 for the little rocket. It costs $200 for the big one to go up once. Parachute time, yeah, okay. You got to get pretty high, and you got to have a pretty hefty shooter. You're not going to get you much stumbling time. Electronic size and weight: ultimately you need a bigger and bigger rocket to boost more sophisticated equipment. Safety requires large recovery area. Downtown Manhattan's probably not a good location. Keep in mind, any of you guys wanting to get into this, it can be a very dangerous hobby. It's a very fun hobby. But there was one story when Triple E first started of it was near a trailer. This particular launch site was near a trailer, and the rocket, the parachute failed to come out. This thing becomes what's called a ballistic missile when the parachute fails to come out. Went through the roof of the trailer, actually impacted their kitchen table and buried itself right in the middle of the kitchen table. Fortunately, it didn't injure anybody. But keep that in mind. If you want to do a rocket, do it safely, do it legally. Next. Future work: what I wanted to do with this rocket, but I didn't have enough vertical space on it, was put a long sector antenna. You guys have probably seen them on cell towers. They go up to 12 to 18 dB, which would buy you about 450 square miles. A lot bigger target area. Unfortunately, my rocket was not quite tall enough for that. Maybe next year. Also, GPS is a nice addition, and a nice small circuit board. We can actually, you know, start to track things. And as the antenna rotates, the idea was to have this antenna pop out of the rocket and just sort of do this, like the radar mast you see on a ship, just sort of rotate coming down, which would give us targets all over the area. Next. Lesson learned: laptops and sunshine do not mix. Dave had a hell of a time. I had a hell of a time. You almost have to have incredible vision to look at a laptop in the bright sun. Rockets without parachutes on ballistic trajectories are dangerous to your health. Number 3, very true: if it can fail, it will. Shooting rockets is a lot like gambling in Vegas. Don't launch anything you're not prepared to lose. And finally, once you push that launch button, you're pretty much done. Here are the websites that were listed. Any of you guys interested in the equipment, the other stuff we used? Next. I'd like to thank everybody, particularly Dave Cantrell, for all his help at every launch, and the ground computers, and the whole Tenacity crew. As you see, a lot of my teammates here helped me out with the video editing, graphics, weather, and the other guys I'd like to thank are Ben Russell and Mike Showalter, who are big into Triple E rocketry and Culpeper, and Caleb of Deliberate Systems. Next. Those are some of the things. If you want to do research about this later, you can look up. It's on the Defcon CD. Next. And that's about it. I'll take questions now. Thank you. Thank you. Yeah, the question we have is there any insurance policy? If you join Triple E, you don't have to worry about insurance because we got our own team of lawyers and our own insurance for all the launch sites. Very, very, very important. Because as you know, if you kill the guy's Corvette next door, he's going to be a little pissed off. Anybody else? Yeah, go ahead. Say again, was I still transmitting? Yeah, it was still transmitting. We had a hard time. We had an Omni antenna actually looking, which did the link, so we really didn't need to aim the antenna. The hard time you see us tracking is Dave trying to hold the camera to see this thing about 2 miles away. I mean, he was doing this freehand without a tripod. Say again? Post-impact recovery? Oh, well, it fell down in a very, for number one, it was behind the house, so you couldn't see the signal. It actually landed behind a suburban house, which was not supposed to happen. It was supposed to land out in an open field, so that's why we couldn't pick up a signal from it. Yeah, we did have mobile stumbling gear. We couldn't pick it up because I'm assuming that the house was blocking most of the signal. Go ahead. Oh, absolutely. Tethered weather balloon people, I think Dave even mentioned model, RC planes and stuff like that. Absolutely. I just happened to be in rocketry, and it seemed like a cool thing to do. Anybody else? If not, I thank you all for coming today, and I'll have the rocket in the next one of the free areas over here. You guys come by, and I'll show you the insides of it. Thank you very much.